so this is a recording for lecture on 17th of June, okay, because the earlier lecture recording has been corrupted, I think, because when I didn't when I upload it to the server of the website, but I believe I did not. I before it finished uploading, then I closed the application. So now this is a re-records. Okay. Okay. So okay. So this one. Okay. Remember last time we are struggling with doing the method one, right? Method. Okay. One. Okay. So the method one says, okay, let's find omega and theta. Okay. Let's look at this point and this point. Okay. The value, it should be the same, right? It should be a. Okay. So this is where n equals to -2. Okay. So this is the n-axis. This is n minus 2. And then this point is n equals to 10. Okay. If you count from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So in short, sir, x minus 2 and x10 is the same. Okay. So if we apply this equation in, here we have a, we can uh, take away lah. Okay, we can take away, right? Um, yeah, so this is a longer way to do it, but we can do it. Yeah. Okay, so we do it like this. Mm, yeah, cos n is -2, so -2 omega plus theta equals to cosine 10 omega plus theta. All right, so n is 10. Okay, so assuming this angle is phi 1 and this angle is phi 2. Okay, so in order for cosine this angle equals to cosine this angle, there is a condition has to be met. Okay, which is so this is negative, right? So this, let's assume this angle is smaller than this lah. So uh, let's say omega 2 is omega 1 plus 2k pi. Okay, right. So why do I write this equation? Okay, um, because of this trigonometry identity, cos theta plus 2 pi becoming cos theta lah. All right. So 2 pi or 4 pi or 6 pi or 0, right? So and so on. Okay. So this cosine is, the value will remain. Okay. It is only if the angle is increment by 2 pi. Right, so similar to this. So this cosine and this cosine is, they are end up having the same value. So the relationship between the angle here and the angle here must be 2 pi in difference, right? Okay, so it can be 2 pi, 4 pi, 6 pi, and so on. Okay, so looking at this, so this is one period, this is another period. Okay, so it is very natural for us to think that it is just 2 pi away, right? So assuming, okay, k equals to 1, okay, so we have phi 2 equals to phi 1 plus 2 pi lah. Okay, so then we put in these equations into here, okay, and put in this equation into here. After you put it in, this theta can cancel off. So in fact, we have -2 omega equals to 10 omega plus 2 pi. And then, wait, this is omega 2, so here is 10 omega. Okay, so okay. Yeah, so it should be 10 omega equals to 2 omega plus 2 pi. Then you can move everything. You got it 5/6 here, right? Guess once you got this, then you could take one of it, okay, and check what is the theta, right? So let's say I pick -2, okay. Wait, I have phone call. Okay, so x minus 2 equals to by this a cosine cosine by this let me okay, a cosine minus 2 omega plus theta. Okay, so x minus 2, the value is a, so a can be cancelled off. So cosine minus 2 omega, we know what is omega already. It is pi over 6. So it is minus pi over 3 plus theta. Okay, so now the question is cosine this angle equals to 1. Okay, so what angle is this? And the angle of minus pi plus theta must be equals to 0, right? Or 2 pi or 4 pi, right? Okay, so and then this one can move over. Then we got pi over 3, right? Okay, so this is the answer. This is the answer. Okay. Well, if in the equations, let's say the omega or the phase that you given is, let's say, you put 2 pi here and then you move it over, then it become another angle, right? It's okay because we know that every pi, okay, the cosine repeats. Okay, so it is okay. You put pi over 3 or pi over 3 plus 2 pi or and so on. Okay, so it will be the same. Okay, the answer would not be wrong lah. You will not be you will not say you are wrong. Okay, right. So let's go to this property one. Okay, so we are talking about the discrete time sinusoids. Okay, so the sinusoid is sample. Okay, it is the cosine wave, but it is discrete time. Okay, so what are those properties? So the first one, okay, um, the discrete time sinusoid is periodic only if its frequency f is a rational number. Okay, so what do you mean by rational number? Okay, rational number means, okay, hang. Yeah, let's give it a second. Okay, rational number means, okay, it is integer divided by another integer in its simplest form. Okay, right? So if you found that the frequency is integer over this small capital F is called normalized frequency, yeah? Okay, which is belongs to discrete time signal. Okay, do not confuse this with analog frequency. Yeah? So this is the frequency meant for discrete time signal. Okay, so how do we get this amber? The this formula that describe the discrete time sinusoids. Okay, so this omega n plus theta, this is cosine. Okay, so you can find the f from here, right? So omega is equals to 2 pi f. Okay, so example, so we have seen that omega equals to pi over 6, right? So that would give us f equals to 1 over 12. Okay, so it is a rational number. Okay, right? So this is an integer, this is an integer. Okay, then the questions now, um, the question now, let's say, okay, do we have f that does it is possible to can we have f that is not a rational number? Seems like everything can be a rational number. 0.5 you can make it into 1 over 2 and so on. Okay, so there are times you might see f is square root of 2. Okay, so in this case you couldn't make it some integer divided by another integer, right? So for this case, if you found that f equals to square root of 2, the sinusoids, the discrete time sinusoid, would not be periodic. Okay, so not periodic. All right, so that is how we determine whether the frequency is periodic or not. Okay, so this is the first way. Okay, there are another way. You can say that it is periodic or not periodic. Okay, so you can use this formula. Okay, you can use this formula. Okay, so if you found a value of n, if there exists, okay, exists a n that you put in there, okay, it will repeat itself, right? So in the previous example, this n is 12, all right? So you could see that every 12 samples, okay, the previous example here, every 12 samples, the value repeats. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and the next 12 will repeat the previous 12 samples, right? So you could identify what is the n. If you could find this value, okay, and you plug it into this equation, it works. You can say that xn is periodic. Okay, right. So the smallest value of n is called fundamental period. Okay, so why n has to be chosen to be the smallest? Okay, uh, so in this example, this n is 12. Okay, can I say n is 12 means every 12 sample points repeats, right? So this 12 sample points is a group and they repeats every time, when n goes along this axis, right? Can I say every 24 point, the samples repeats? Can. Can I say 36 points, every 36 points the sample repeats? Also can. All right, it's also true. Okay, but normally we would say, okay, we want to look for the fundamental period where n is the smallest group that it repeats itself. So in this case, it's 12. All right, it's 12. Okay, right. So that's the meaning now. Okay, so proof of periodicity property for discrete time sinusoid. Okay. Uh, okay, so how do we prove it? Okay, we start from here. Okay, xn plus xn. Okay, let's say xn is given as a cosine omega n plus theta, right? So we put this into here. Okay, then it will be a cosine omega. So n is n plus n now, and then plus theta. Okay, equals to a cosine omega n plus theta, right? Okay, x n plus n is this, x n is this. So a can be cancelled off. Okay, so again we come back to cosine this angle equals to cosine this angle. So these two angles must be 2 pi away, right? So omega n, let's multiply in first. Omega n plus uh, omega n plus theta, okay, equals to cos omega n plus theta. Okay, so in order for this angle and this angle, we put it in there. The cosine of those angle give you the same value. Okay, so it means that this omega n, okay, must be multiple of 2k pi, right? So it's just like previously. Okay, so this the previous explanation now. So this must be a 2 pi, 4 pi, or 0. Then this left and right will be equivalent. Okay, so it must be a value of 2 pi, 4 pi, 6 pi, and so on. In short, it is 2k pi now. So k is the harmonics number. Okay, so we could write here uh, omega equals to 2 pi k lah, divided by n lah. And then omega, we all know that it is 2 pi f. Okay, so this 2 pi and this 2 pi can cut away, and f is k over n. Okay, so if you look at it, okay, this is an integer, must be an integer. Okay, uh, and so this is periodic, right? So therefore we have this saying now, f must be a rational number. Okay, must be a rational number. Okay, right. So we got this. Okay, So to determine the fundamental period n of a periodic sinusoid, yeah, we express k and n relatively prime. Okay, right. So the example here, f1. Let's say you have a sinusoid with normalized frequency f1 31/60. Okay, so from this number, you could see that the bottom one is 60. Okay, what do you mean by n equals 60? It means that every 60 points, okay, every 60 points, the groups repeats, the sample points repeats. Okay, so for f2 equals to 30/60, okay, if you simplified it, you will get 1/2. Okay, so you simplified it until k and n are relatively prime, and then you would say that for this normalized frequency sinusoid, the n is 2. Okay, so every 2 points, the sample repeats. Okay, so that is the how we do it lah. Okay, so how we justify. Okay, and most of the case you will see a very nice number like 1/2, 1/12, 1/100. Okay, so if you have something like this, okay, is you are picking a sample point that is, I mean, you are picking the sampling frequency or the sampling interval that is not is not conventional, right? So it depends on how do you sample it. You will end up with, you will get different f. Okay. This one you can see, you can do a revision on tutorial 1, question 2 to check how does different sampling frequency give you different normalized frequency. Okay, right. So that is tutorial 1, question 2. Okay, let's move on to property number 2. Okay, discrete time sinusoid whose frequency are separated by an integer multiple of 2 pi are identical. Okay, so what does that mean? Uh, so what it means is that this now. Okay, let's say you have omega now. So you have xn equals to a cosine 2 omega plus theta. Okay, so let's say you decided to increase this normalized frequency by 2 pi. Okay, then this is x1n, then you decided to do like a cosine 2. I want to increase the normalized frequency by 2 pi. Okay, and then you will plot x1, x1. Okay, looks like this. Okay, and then when you plot x2, okay, this is n, this is n. Okay, you will also get the same pattern. Okay, so that's what it means. Discrete time sinusoid whose frequency are separated by an integer multiple of 2 pi are identical. So this x1 and x2, the pattern is identical. Okay, if you plot it on n. Of course, if you plot it on t-axis, the time axis, uh, probably this is narrower, this is wider. Okay, but the computer doesn't really care. They just look at how many samples you comes in. Okay, so so this is the property. This is property number 2. Okay, so if the omega, if you increase by 2 pi, the same pattern repeats. Okay, so in other words, you can think this way. Okay, so let's say this is 0 pi minus pi. This is a 2 pi length. Okay, the length is 2 pi lah. Okay, so then you decided to have a omega here. Okay, then 2 pi away, there will be this guy here. Okay, so this is omega 1, this is omega 2. Okay, if they are separated by 2 pi, okay, if you put this frequency into the cosine, you will get this pattern. You put this frequency into the cosine, you will get the same pattern. Another 2 pi away, omega 3, okay, which is 4 pi higher than omega 1. You put it into the cosine, you will still get back the same pattern. Okay, so this group of frequency here is like they are photocopy. They are the twins, brother or sister to omega 1. Okay, so this is the property 2. Okay, so let's look at the proof. Consider signal cosine omega naught n plus theta. Okay, now I wanted to increase the omega by 2 pi, right? So like this, okay? Right, so after we increase it, this one we multiply in, then we get omega naught n. This one is 2 pi n, okay? So cosine omega n plus 2 pi n plus theta is equals to cos omega naught n plus theta. Right, so this is the trigonometry identity. Okay, trigonometry identity say cos 2 pi 2 pi k plus theta equals to 2 pi cos theta. Right? Cos theta equals to cos theta plus any 2 pi, like multiple of 2 pi. Okay, 4 pi, 6 pi, it would still go back to cos pi. Right, so this one essentially you can remove from the angle. Okay, and then you get back this one. Okay, as a result, all sinusoid sequences uh, uh, we can say all sinusoid sequences with omega k, where omega k is omega naught plus 2 pi, omega naught plus 4 pi, k is 1, 2, 3, 4, 5 now, 6, 7, 8, 9, 10 until infinity, in fact. Okay, so when you have a frequency of 2 pi putting in here, all these x1k, x1n, x2n, x3n, x4n, they are all is indistinguishable, or in other words, they are identical. All right, so you can't distinguish them. Okay, they are indistinguishable. All right. Okay, so any sequence resulting from a sinusoid with a frequency omega, okay, greater than pi. Okay, so meaning that this, you have to know how to draw this. So this means minus pi to pi, omega is greater than pi, meaning there are some frequency over here. Okay, so a sequence resulting from a sinusoid with frequency with omega greater than pi, whether they are the frequency is here, this region or this region, or f equals to 1 over greater than 1 over 2. Okay, so this is omega axis. Okay, if you plot f axis using omega equals to 2 pi f, okay, you can plot here pi actually is correspond to 1 over 2. Here is correspond to minus 1 over 2. All right. Okay. Okay. As if you have frequency outside of this minus pi to pi, or outside of this minus half to half, okay, this region, okay. Uh, so those sequences are identical to a sequence obtained from a sinusoidal signal frequency smaller than pi. Okay, so there will be a similar frequency that can inside this region, okay, that having the same sequences. Then you use the frequency outside of this, we call it fundamental region, okay, fundamental frequency region. Okay, all right. So you might ask, okay, so should I use this frequency or this frequency, or no, 4 pi away another frequency to write my equations or to construct my discrete time sinusoids? Uh, the the best answer is always fall back, okay, to the smallest angle. Okay, always fall back to the smallest angle. Meaning that if your frequency is greater than pi, okay, you can always uh, subtract 2 pi from it, and then found another frequency that would be having the same sequence. Okay, then this sequence now. Okay, so that is the meaning. So we can always reduce our frequency, okay, into here, okay, minus pi to pi. Okay, so that is property 2. Okay, because of this similarity, we call the sinusoid having the frequency omega greater than pi and alias, okay, of a corresponding with frequency omega smaller than pi. Okay, so we call those twins brother that give us same sequences and alias. Okay, so this is minus pi, 0, and pi. Okay, so you have frequency omega here. So 2 pi away, 2 pi must be 2 pi. You have another guy, okay, higher frequency than this. Okay, this is aliases. Okay, this is aliases, right? This is um, the original, okay, the original. Okay, so here we call it fundamental, fundamental frequency range. Okay, right? So you will have a lot of aliases. Maybe here, okay, another 2 pi away, another aliases. Similarly, another 2 pi away, you have aliases 2, okay, and so on. Okay, every 2 pi generate from here, right? Okay, so this, okay, we regard frequency in the range minus pi to pi or minus half to half as unique, and all frequency omega greater than pi, okay, or f greater than half as aliases. Okay, so the frequency inside here are unique. Okay, within this region you couldn't find any two frequency that give you the same sequences. Okay, so if you plot frequency with this value, I mean you plot sinusoidal discrete time sinusoid with this frequency and this frequency, you will see that the pattern would not be the same. The sequences would not be the same. Okay, so so in the frequency in this range, they are unique to each other. Okay, but if you go outside, then you will find identical twins. Okay, so notice the difference between discrete time sinusoid. Okay, so for discrete time sinusoid, we will restrict, okay, our frequency between minus pi to pi or minus half to half. Okay, so we use minus pi to pi because the no normally the signal we works on is symmetry lah. Okay, so they are symmetry around 0. Okay, so it is convenient to use this range of frequency. Okay, you might ask, from minus pi to pi, the length of this spectrum is 2 pi. Can I use omega from 0 to 2 pi? The answer is yes. Okay, so you still can get the answer. Okay, but it's just that the calculations might be a bit different, the steps, but the answer would be the same. Okay, right. So this is just for conveniences for our calculations, because signals that we deal with are normally symmetry around 0. Okay, so for continuous time sinusoid, in other words, analog frequency. Okay, the frequency f, capital F, you see, this one is capital F. I forgot to change it again. Okay, so the capital F, or omega equals to 2 pi f in radian. Okay, their frequency range are infinity. Okay, so analog is like this, discrete time is like this. Okay, move on. Property number 3. The highest rate of oscillation in discrete time sinusoid is attained, okay, when omega equals to pi or omega equals to minus pi. Okay, uh, or equivalently f equals to half or f equals to minus half. Okay, so can I say that? So can I say what is the high frequency component here and what is the DC component here? According to this statement, they say that if you increase your omega towards pi, okay, this region here is high frequency region, and here is DC. Okay, if you move it to the left, then you are approaching DC, okay, a low frequency region. Okay, and then since they are symmetry, okay, so this area is high frequency, and if you move it over here, omega can be negative, this is positive omega, this is negative omega. Okay, so if you push it over here, then it will be um, go towards low frequency. Okay, so this is minus omega, this is omega. All right. Okay, so so f half, and so if you change this omega axis to f, okay, and you use 2 pi f, omega equals to 2 pi f, okay, you will find that corresponding to minus pi, here is minus half, this is 0, this is half, like that, okay, therefore you, so these sentences here. Okay, consider xn equals to cos omega naught n when frequency varies from 0 to pi. Okay, so let's try omega 0, omega pi over 8, pi over 4, until pi over 2, until pi. Okay, so their corresponding f is 0, 1 over 16, 1 over 8, 1 over 4, 1 over 2. Okay, so let's look at the graph. How does it look like? Okay, so if you increase the omega from 0 to pi, you will find that when omega equals 0, then this looks like a DC. Okay, slowly increasing it, so you will have slightly oscillation between sample, a slight oscillation between sample. Further increase it, greater oscillation between sample. Again, much higher oscillation between sample, and this is the highest. Okay, so this is the rate of oscillation. Okay, so when omega increase from 0 towards pi, you will see the rate of oscillation, okay, is also increased. Okay, so that is the meaning here, right? There's the meaning here. Okay, so the and then from here we could see that this is the n. Okay, so every 16 point it will repeat, every 8 point it will repeat, every 4 point it will repeat, every 2 point it will repeat. Okay, so for DC, n is infinity. Okay, because you don't have a group that would repeat itself. Okay, but this is arguable because can you say here every single point it repeats? Okay, also can now, but the reason is we are talking about sinusoid. Okay, so it has to be some group of points that repeats now. Okay, so here we say there is no groups that repeat itself now, but okay, so normally you don't see this case very often. Normally we'll deal with things like this lah. Okay, we know that the period of the sinusoid decreases as the frequency increases, right? This is the period. Okay, we call it fundamental period. Okay, okay, so the period decreases when the frequency increases, right? Also note that the rate of oscillation increases when the frequency increases. Okay, rate of oscillations, you can see this from this graph. Okay, move on. To see what happens for omega naught from pi to 2 pi, we consider sinusoid frequency as follow. Okay, so we already know that, let's say we wanted to only look at this fundamental, right? Fundamental range, right? So what happened from pi to 2 pi? Okay, what happened from pi to 2 pi? Okay, let's do some calculation. Let's say you have omega 1 is between pi to 2 pi. So let's say you have one guy here, omega 1. Okay, and then you have a omega 2, which is omega not negative. Okay, omega not negative is here lah. Maybe this is minus 2 pi, maybe this somewhere here. This is omega 2 negative, and then plus 2 pi. Okay, so 2 pi away from here is, let's say this is 1 pi, maybe here. Okay, so this omega 2, right? Maybe somewhere here now. So in this range. Okay, so add 2 pi. Okay, it will go, if you are here, 2 pi, wait, 2 pi. If you increase, but then it will end up 0. Okay, if you push it here, yeah, it will be slightly over 0 here now. So I draw it too much over. Okay. Right. Okay, so never mind, but it is in this range. Okay, so let's do some calculations. Okay, let's say we define x1n, it will be using this frequency. Okay, we put in omega 1 inside here. Okay, since omega 1 equals omega naught, so so you end up these equations. Okay, that's x1n. Okay, x2n. Okay, we want to use the frequency x the omega 2. Okay, which is this equation. We put it in. Okay, remember, if you have in this bracket, if the angle, we have we can always subtract out 2 pi, or if there is 2 pi, 4 pi, 6 pi, we can always take it away. Okay, or replace it with 0 also can. You can say it this way. So we end up this one. Okay, 2 pi is no longer there. And then because cosine is symmetry, so we can say cos theta equals to cos minus theta now. And so the negative can also be taken away. So you'll find that this and this is the same. Okay. All right. So hence omega 2 is an alias of omega 1. Okay. Right. So they are, one of them are aliases. Okay. Um, Normally we would say this one because they are considering here, and but they are saying this is the aliases. This is not the aliases original. But in the normal convention now, we are saying, okay, yeah, whatever inside here is unique. Outside, those are called aliases. Okay, but in this case, because we are talking about, let's talk about this as our unique frequency range. Okay, so whatever outside here is called the aliases lah. Okay, but this is just for this example. Okay, this for this example. Okay, not too much worry about what the term. Okay, whether this is the aliases to this, is the aliases to this. In fact, you can freely say, okay, this is alias or this is alias. It's okay. Okay, it's understandable. It means that they are identical. Okay, when they are putting into the discrete time sinusoid. So no worries. Okay. So if we had used a sine function instead of cosine, okay, let's say this is we change to sine, the result would basically the same except for a 180-degree phase difference between the sinusoids, x1 and x2, meaning that x1 and x2, there would be a difference, okay, but one would have 180-degree phase, extra phase, okay, meaning that here would be plus pi. Okay, but adding a phase, okay, to this sinusoid, it's just that the waveform has been shifted to the right. Okay, if it's plus, okay, on minus, then shift to the left. Minus is shift to the right, positive shift to the left. Okay, but the pattern remained the same. Okay, so the pattern remained the same, just that no one is delayed by pi or advanced by pi only. Okay, so strictly speaking, the pattern is still the same. Okay, pattern are still the same. Okay, so in any case, okay, as we increase the relative frequency omega naught of a discrete time sinusoid from pi to 2 pi, its rate of oscillation decreases. Okay, let me redraw that. Okay, so they found that, okay, if you increase the omega from this point towards 2 pi, you found that the frequency, the rate of oscillation decreases. Okay, that makes sense because this is 0, which is DC. Okay, okay. In terms of in the aspect of sine and cosine, cos 0 and cos 2 pi is the same. Okay, so here would be also a DC. All right, they will also DC. Pushing it towards here, you are approaching lower rate of oscillation or low frequency. Okay, all right. So here, so pushing here, if let's say your omega is over here, okay, so you were pushing here to approach DC lah. Okay, so you can see that this is like a mirror. Okay, so here and here is like flip. Okay, so this one going to the right, then you approach DC. This one would be going to the left. This component should be going to the left, then you could approach DC. All right, so that's the so this pi here is like uh, a mirror lah. It's a here, the component here can be fold over here. You fold over here, then the operation will be the same. Okay, right. For omega equals to omega naught equals 2 pi, the result is a constant signal as in the case for omega naught equals to 0, right? So this one understandable now. Express xn in exponential form, okay? So cosine, okay? According to Euler's formula, okay, go and check it. Cosine can be expressed into exponential j theta and exponential minus j theta. All right, so that's formula for cosine. Okay, so and it is very useful to express cosine into or sine into exponential. Okay, but because in any case you need to multiply signal, cosine multiply another cosine or cosine multiply another sine. Okay, if you do not have the table of trigonometry identity, then it is very difficult to do. Okay, but if you are doing multiplication of exponential, it's very simple. Okay, it is just the angle addition and subtraction only. Okay, right. So many cases you would like to change cosine to exponential form. Okay, and then we will do the mathematical calculation starting from here. Okay, right. Since discrete time sinusoid signal with frequency that are separated by an integer multiple of 2 pi are identical, it follows that the frequency in any interval omega 1 until omega 1 plus 2 pi constitute all the existing discrete time sinusoid or complex exponentials. Okay. Usually we choose the range 0 to 2 pi or minus pi to pi, which we call it fundamental range. Okay, so what this sentence means is that um, okay, let's say uh, this is pi, this is minus pi. Okay, you have a cosine which you use this frequency. Okay, for your sequences lah. Okay, and then you found that after you do the exponential, convert this into the exponential form. Okay, in fact, you'll find another negative frequency here, right? Okay, and then this amplitude is a, then the amplitude has to be uh, decreased. Okay, so so this is so what it says that okay, instead of looking at this part okay, the other part automatically will be there. Okay, this will be automatically exist. Okay, um, when we are dealing with exponential. Okay, okay. In other words, let's say your xn is x a cosine omega m plus theta. Okay, so probably when you draw the omega, you only care about 0 to pi and so on. Okay, so you have an omega here. Okay, but in fact cosine is symmetrical lah. Okay, so whatever here, okay, will be uh, reflected here also. Okay, minus omega. Okay, so instead of working on cosine, okay, it is better to work with this exponential lah. Okay, so uh, so like this is amplitude. Okay, so this is minus positive omega and minus omega. What I want to say here is that in fact, in order to reconstruct cosine term, this is a real signal. Okay, so you need uh, complex number which are conjugate. Okay, exponential j theta is complex number. Okay, remember complex number. Okay, is can be represented by a plus jb. Can also be represented by phasor form, and the other one is you can represent it with EJ data. Okay, they are these are all three forms of complex number representation. Okay, they are interchangeable. Okay, so in this course we are mostly dealing with this lah. Okay, right. So what you wanted to say is that let's say you have this signal. Okay, using Euler formula, you found that you have component of omega and minus omega. Okay, so in fact, whatever frequency you have there, there will be a negative frequency exist needed to be here. All right, so this frequency length of 2 pi uh, is unique lah, is essential, and it is we call it fundamental frequency range. Okay, fundamental range. Okay, so we will restrict our explanation or the calculations or uh, all the description. I mean, in the future chapters also. Okay, we will work our way only limit to minus pi to pi. Okay, so it means that if you are given with omega which is out of this range, there are always okay you can subtract 2 pi, okay, and bring the frequency back to here, and then we will do the calculation using the frequency in this range only. Okay. All right. So regarding cosine and this EJ data, E minus J data, we could see this in the future section now. Okay. We'll see this more. All right. So what actually this sentence is saying is that um, a cosine functions, okay, actually consists of positive omega frequency and negative omega frequency. Okay, so this frequency component, these two complex number has to be there in order to reconstruct a cosine. Okay, so you have to you have to use the frequency component at this side and also the negative side. Okay, so that's what it means. So for that, then this length has to be 2 pi. Okay, so with this 2 pi, okay, 2 pi length of frequency range, it will be this range will be constitutes all the existing discrete time sinusoid frequency and complex exponential already. Okay. Okay, so this is the lecture, re-recording lecture, and we stop here lah, and we'll continue the next lecture in the next video recording. Okay, thank you.